Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at using matrices to solve least squares problems. So let's start with this question. We're going to calculate the regression line for these points here. So because we're looking for the equation of a line, and a line always has this form, we know we're looking for m and b. We can turn this into a system of equations. So from our first point here, 1, 7, we have that y, which is 7, equals m times 1, m times x plus b, and we can do similarly for the next point. Y equals m times x, here x value is 2, plus b, and then we do similarly for the last 3 points. So we've seen before how we write such a system of equations in matrix form. We set up our first matrix, and that's the matrix of coefficients. So in each of these equations, the coefficient of b is 1. So I'm going to put 5 ones there. Now I'm going to put the coefficients of m in the next column. And then we put our variables in the next matrix. Now, because this first column was the column of b values, b has to go first and m will go second. And I want that to equal all of the y values. So the y values being 7, 10, 14, and so on. So this is usually written as x times beta equals y. Now we know that there won't be a unique solution b and m to this system unless it happens that all of these points lie in a straight line. It's pretty easy to see they don't lie in a straight line. So there isn't going to be one solution bm. So what we're going to do is try and find the least squares solution for this vector. Now how you do that, you multiply at the front by x transpose. Of course, what you do to one side, you need to do to the other. So let's go ahead and calculate x transpose x. So here we have 2 by 5, 5 by 2 matrix. The resulting matrix will be 2 by 2. That's nice. We've taken much bigger matrices and reduced them to 2 by 2. So using our across by down multiplication, we have 5, 15, 15, 55. Okay, the next thing we need to do is calculate this x transpose y. So again, using our across by down, we get the vector 54, 173. So we have completely transformed this system of equations. Let's now solve that. So these are the matrices we obtained on the previous slide. Now this is an easy system to solve. We can just multiply at the front by the inverse of this matrix. So remember that the inverse for this 2 by 2 matrix is 1 over AD times BC, which is 275 minus 15 times 15. It's 1 over 50. And then we switch around the elements on the leading diagonal, and then we change the sign of the other two elements. So this is the inverse. If I multiply x transpose x by its inverse, goes away, I'm just left with this. And then of course I have to multiply this one here with this matrix at the front. So doing this by hand, I think it's easier to multiply the matrices first. We get 410, 35. So that becomes 8.2, 0.7. So we wrote it so the top number here was b, the intercept, and the bottom number was the gradient. So our regression equation is y equals 0.7x plus 8.2. That's exactly the same answer we would have received if we used the formula and calculated covariance everything to find the least squares regression line. Let's take a second to figure out why this works. So we want to solve this matrix equation here. We saw in the last example that x wasn't even a square matrix. Sometimes x just doesn't have an inverse and there's no solution beta. So what we want to do is find the beta that is as close as possible. So remember that the column space of x is the span, that is the set of all possible linear combinations of the columns of x. It turns out if you multiply x by beta, you will get a vector that is in the column space of x. So which such vector is going to be closest to y? So we're going to define r as the residual vector. It is x times beta minus y. This quantifies how close we are. This will just be a vector, and each of its entries will be the difference between this and the entry in y. So this all works because it turns out the vector x beta that is as close as possible to y, it turns out to be orthogonal to every column of x. So r has to be orthogonal to the columns of x. This means that x transpose times r gives us the 0 vector. When you multiply x transpose by r, you are simply multiplying the columns of x, which are the rows of this matrix, by the entries in R. And orthogonal dot product has to be 0. So if I take this equation here and I multiply at the front by x transpose, I get this. But because this has to be 0, I can substitute this for 0, and I simply get x transpose x beta is equal to x transpose y. Now to solve this, we have to take the inverse of this matrix. The good news is that in most applications, this is invertible. It will be invertible as long as the columns of the original matrix X are linearly independent, as they were in our previous example. So let's see how we can use this in an example of nonlinear regression. So we're going to have a look at log linear regression. So that's where you're not finding a linear equation linking x and y, you're finding an equation of this form. So as the name might suggest, we're going to use this when it looks like the data lies along something that approximates a log curve. This is great for modeling productivity, things you can do. So, for example, you go to the gym, the amount of weight that you can do starts increasing a lot more when you start, and then it tapers off. Or perhaps you're learning a new language, and the number of words you learn a lot at the start. You probably already know some, you learn quite a few at the start, but it tapers off. So we'll perform a log linear regression on these 4 points here. We're finding an equation of this form that minimizes the error, minimizes the squared distance between our function and these points. So you can see the y value goes up by 10, 6, 2. The y value is increasing at a decreasing rate. That's how we might know to perform log linear regression. So the idea behind this is we know that y equals log x is a curve like this. But if you change the y scale so it's logarithmic, here it's going up by powers of 10, then this function is actually a straight line. So what we're going to do is perform a linear regression between x and not y, but the log of y. So here are our x and y values. Now what we're going to do is take the log of y. Now usually in this we use the natural log of y. We have to use natural log if we want it to be e to the power of. So each of these values was obtained by just taking the natural log of this y value. Now if we look at our equation here and we take the natural log of both sides, on the left hand side we get natural log of y. On the right-hand side, we get natural log of a plus bx. So we're going to draw up our matrix x to reflect this. Our matrix will again have a column of 1s that represent the a, and because this is b times x, we put each of these x values in this column. So then, of course, x transpose will be this. So calculating x transpose x, we're just going to use our across by down again. We get this matrix here. Of course, we need to calculate the inverse of this matrix. And so AD minus BC, 56 minus 36 is that. Then we switch the entries on the leading diagonal and change the sign of the other two. So our matrix Y is just all these values here. So all we do now is we take this and multiply it by x transpose times y. Now when we get this, we get our 2 by 1 vector. So this number here isn't a, this is ln of a. If we want to find a, we raise e to the power of this number. So e to the power of 3.95 is about 51.94. So our equation here is going to be y equals this number for a, and then b is just the same as it is in that vector. So it'll be e to the power of b times x, and we're done. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.